Yeah, so hello everyone. Nice to meet you all again. Please let me know who you are in the chat so I know which one of you I need to remind that this stuff is important because you're doing your thesis and all sorts of research, or maybe some of you are just interested in deep learning in general. So today I was intending to do the instance segmentation, but I will do that next time. So today we'll do the recurrent neural networks, the very beginning, because I know at least some of you have some research going on where you need to do time series. So either for some of you are doing classification of the music, some of you are doing the predictions of the weather and other things, so that could be useful. You could add RNNs to any other models that we already know. So just again, reminder, please let me know in the chat who you are here, and we'll wait a second and then we'll start. So in the Jamboard, I mean not in the Jamboard, but in Google Classroom, I will open the task 16.2 where you will have the template. So the template will be necessary for today's work. And I will open the template myself as well. So I am opening the template, zooming in, sharing the screen. Just a second. So yeah. So this will be the template, I guess, right? I will explain in detail some of the things that are a little bit different than before, and also the model itself. So we'll start by, okay, I see we have some hellos going on. That's great. That's great. That's great. So, are templates ready? So for now, just listening. Okay. Cool. Anyway, so is template ready to work? Plus minus. You have it in the Google Classroom. Plus, I will also drop a chat link in for the template here in the chat, just in case somebody is doing this without the Google Classroom. Just a second. Okay, I closed my Mega Drive. That was not a smart move. Meanwhile, those of you who have access to the classroom, please check in. So I have problem uploading the stuff, but I will add it later to the video. Anyway, if any of you not able to access the template, let me know in the chat. I will try to get it to you somehow. But if you not following with the code, then it's fine as it is. So okay, let's start by examining a little bit the code. I will drop in probably the link a little bit later because my Mega Drive wanted to sync all of my stuff at the right moment when I'm having the live session. That's great. So anyway, here, so we have two additional libraries here. maybe those we did not use extensively before. So they are just like really simple tools. You can press here on terminal, where you open your environment, and then you can just type in pip install tqdm or the argparse. You can even write them, I think, in the one line, argparse. So, and that will install those libraries if you don't have them. But if you have them, then that's fine. So then there is the argparse thing. So the argparse thing is great because you can pass different kind of parameters and all sorts of stuff by every time you execute the script. Because as you know, in machine learning, nothing works with the first time. You need to try different learning rates, batch sizes, architectures. You can pass them as arguments. And to do that, let me share a little bit the screen as well. So I will share it in this way. So if you go here and press the edit configurations, or you can do that, of course, from the console as well, then you can just drop in here, for example, batch size as 16 or something else. You can try out different kind of hyperparameters just by passing different parameters to the console. So that's why it's very nice to use this kind of tool. Then, if you go down, there will be a couple of to-dos that we will need to do today. So one is to implement some kind of periodic function. In the very beginning, I think we will just implement the sinusoid. Then later, when this is going to work, we can add something more challenging for the model. And in general, the idea will be the modeling task. So we will try to predict the next step of the function depending on the previous steps. And here will be the RNN cell. This will contain some learnable parameters, some weights and biases. And then there will be the equation for the cell. And this is going to be the one layer vanilla RNN, single layer. So that means that there will not going to be multiple hidden states. There are going to be just one hidden state, and we will roll it out here. We'll go step by step. And then in the bottom, we'll have some extra rollout that I will explain a little bit later. So there are few places with to-dos. If you go back to the Jamboard here, we'll check if I can finally have, no, my Mega Drive is not working anymore. Actually, the Mega is really cool, but not today. So anyway, lost my window. So this is very simple schematic of the RNNs. So the RNNs, the axis here, they are the inputs. So for the sinusoid, if you have just a sinusoid, we have one-dimensional input, right? Just at every time step, what will be the amplitude, right? Is it negative or positive? And that means that, for example, at time step 1, we'll have 1 amplitude. Time step 2, it will be a little bit higher, 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 then lower, 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 higher, 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 stuff like that. So those are the inputs, right? The outputs can be anything, basically. In this time, we will do the modeling task. So there is also a thing called language modeling that we can explore maybe in later sessions, is that you can predict the next word in a sentence, for example. If you have the first words in the sentence, and you predict the next one. You can predict, of course, like some of you are doing research with weather, you can predict what will be the weather next time. And you can also do the pooling of all of these and do the classification. For example, what is the sentiment of this sentence? Like, is it positive or negative? You will just pool all of the outputs together and make an average of them, for example, and pass to the fully connected layer and then do the classification. That's another way. Some of the important things that you need to notice here, and I will maybe I'll add also the equation immediately. So the equation of the vanilla stuff is actually something like this. So they usually use it with a tan H, so hopefully it will I can copy it quickly. If not, I will write it in LaTeX. So yeah, not like a little bit blurry. Sorry for that. So the equation is like this. The inputs are x's here. The outputs are actually the h's, but here they are o. So that means that you can add some kind of function on top of h to have the o's. Maybe you can even write it down a little bit clearer, otherwise it might not be that clear. Let me find my LaTeX typer. So let's try to write it as it is in this kind of the equation, as it is written here. So there is actually also the weight matrix, right? There is U matrix, and then there is also V matrix. So V matrix is like a linear projection. So that's a simple linear projection. So let's write it down. You were saying that inputs are like sinusoidal. That means what? So you will understand that in a minute. It like the sinusoidal inputs is just the like very dumb example for what we're gonna do. It doesn't mean that it shouldn't. So the inputs here can be anything. So it could be like your encoder from the DenseNet or ResNet, for example, for the encoding of weather maps. And then the outputs could be, again, decoder for the weather maps. So it's not tied to some specific input. It can be anything. It can be language. It can be images. It can be like videos, you know. So, but just a second, I will clarify the equations. So I don't like that my equation is different than in this picture. So just a second. So yeah, let's try to write in LaTeX this equation correctly. So here will be the h at point t. Let's see. Okay, I'll make it bigger so you know how to write in LaTeX as well. That's a good skill. Tan h. Then the first one will gonna be the U matrix. So the U matrix will be a dot product. So C dot, or you can actually leave it as is, but let's add the dot product there. So with xt and then plus weight matrix, weight C dot ht plus there is not written here, but usually you add bias as well. So the bias param, right? So we'll have these guys, and then the output stuff will be the OT. Let's add also these lines. OT will be the linear projection, basically, and that you know very well, right? You know how to do linear projections, right? C dot DHT. And here we again could add some B, basically BV, and here let's call it BW, right? So LaTeX it. Right, so that's beautiful LaTeX. So yeah, guess hopefully that's fine. If you see some problem, then say, okay, so I will copy this as an image and now drop it in the Jamboard. So that's much better, right? So this is what it is, basically. And the logical question is then, what is the h then? Because in the very first time step 0, the h is not defined, right? So the h in the very first time step will be 0, and then in the next time step it will contain some kind of memory, basically. So every time when we move on in our sequence, the h encodes the memory. So basically this is like your memory vector. So this tan h makes it a little bit complicated because that's from the -1 to 1, so it's not really completely free memory, but it is nonetheless the memory. And then the output projection is something that we project out to some kind of, let's say, the inputs are in one dimension, the outputs we want another dimension. And the fun thing is that we could also feed the outputs inside the inputs. So let me show you. So we could like feed this thing inside here and get out the next prediction, right? So maybe it's, let's color with some other color. So we get the next prediction, and then the next prediction we again can feed into the model, and then we can get again the next prediction. And basically we can do this with some rollout distance that you want, like this, some extra sequence ahead of the time, and you don't need any ground truth here. So you can just roll out as many of these as you want, but of course the output will be degraded. So there are some more advanced models than vanilla RNNs that will work better, but I hope you get the idea that you can feed in the outputs inside the inputs if these outputs are the same dimension as the inputs, and they basically are trained in order to predict the next time step. So that will be the, let's say, modeling task or language modeling task, that if that is for the language, and you can like, for example, type in a few sentences and then you get the predictions. This is actually the same thing as Google does when you type in some of the words, and it gives you some other options to choose. So it feeds in some of the first words and then tries to predict the next words. So what you have, so should ht minus 1. Oh man, I did the wrong equation, sorry. You're right, interesting that I did not notice that ht minus 1. So mathematically, programmatically, that might be okay, what I wrote, but mathematically that was not okay. Just a second. If you notice some other inconsistencies, let me know. So there should be ht minus 1. So what I just changed is this one term here. So this is from the previous time step, of course, not from the current time step. So the far side, first line, first line. So this is, I guess, the 0, h, then there is t. So there is actually t minus 1, t plus 1. I don't know, like, I don't know why they did this, these kind of notations, but basically this is what it is. So I will also give you some other pictures to think about it a little bit. Just a second. So the next slide. And then we'll start coding this stuff, basically. And then you will see beautiful renderings. And then we'll make some interesting periodic functions. So you have different ways how to train these, any of RNNs. There are also some other ways. So like basically the, let's start writing out what would be the go-to methods if you would like to do your RNN models. So let's say modern RNNs, the ones that you should know about, and basically if we have time we can look at them. There are LSTM, long short-term memory cells, and then there's GRU cells, and then there are phased LSTM cells. Those are quite powerful. Then there are layer norm LSTM, and of course there are those would not be really LSTMs, the RNNs, but there are transformers. They are attention-based models, transformers. But also you can add basically the attention mechanisms to the LSTMs itself. So there could be some kind of attention LSTMs. I bet there are a lot of them. So basically these would be some of those that you could use, and the training methods also are different. So one is that you can, I know, like probably this one is not that relevant, maybe in some case. So what you can have is, let's say, one input, and then you just predict all sorts of outputs. So just one word as an input, and then two additional, like not two, but three additional words as an output. You can also have like a sequence that you input and then predict only the next step. And why this is important is because the error, so when you calculate the error here, the like the ground truth, that is super important. If you calculate the ground truth only from this method where you have like one predicted output, this is super bad, because your ground truth will be error only here, and then it will go to the previous cells with very weak signal down here. So much. Also, this method is bad. This is bad. This is bad. This might be working, and this is basically the standard method for the most cases. The idea is that for every time step that you feed in, you want something to have the error gradient coming here for the backprop. If you like don't have for every time step the error gradient, it will be very hard to learn anything in these kind of models. But once you learn the model, when you have finished your training, then you can apply it in any of these combinations. It will work with any of these combinations most likely. So Christopher is asking, GPT-3 model architecture is built on transformers, right? That is true. GPT-3 is a little bit simplified version of those original transformer models. Basically, but they have also quite a significant problems. I have made transformers multiple times from scratch. There are significant problems of training them. The repeating words or repeating, let's say, the outputs. That is also a problem with transformers. There's a lot of problems with them, but still they theoretically are quite powerful models, and basically they showed that they can handle very long sequences because they actually don't have memory as like RNNs. They just pay attention to things. So RNNs have memory. Transformers have not exactly memory, working memory. They have memory from how to handle like from the data set on which it was trained, basically. So how to handle data, the logic. Here's another image. So there's again the time steps, and I'm showing these images multiple times because I want you to remember and understand, because I have seen the students sometimes don't understand it, is that the weights, so the orange box of weights, and that's the same also in this here, this is the same for all time steps. This is not different for every time step. It is always the same. And the H vector is in the beginning something else, and the end something else. So it is your memory that is kind of running through the sequence, and this is different for every sample. Like it's not something that is same for all samples. This is different for every sample, the memory, but the weights are same for all samples and same for all sequences. And the inputs, of course, they are the sequences are different for every sample as well. Okay, so a lot of pictures, equations, some very simple equations, stuff like that. Let's move to the code. So I will try to also give time for you to code stuff. So I realized that I'm missing some of the information needed to complete the tasks, some of them. Just a second. I will check if my... No, okay, cool. So here, let's make an sample of the of the sinusoidal function. Let me check if I'm sharing the screen right. Yeah, with 5,000 samples, if I remember correctly. Let me double check. Don't want to make it too different from what I tested before. like this. Also, I guess I finally have the link available, except I cannot close my file. What is this? So, okay, I will drop the link to the coding template inside the chat if somebody did not get it. So, what is this? This is not what I wanted. So when are the weights updated then? The weights are updated at when we call the backprop, and then we do the weight update function, if you remember, and that's basically the same training procedure as always. Maybe the one thing that might be confusing, and I think in the very beginning of this course, so this is going to be the coding template, is that the gradients for every time step is summed together. So I mean the error is not recalculated on every time step. It is added to the gradient with a plus sign, basically, and this is done automatically by Pytorch. It is done automatically by TensorFlow and all sorts of those libraries. So let's clarify a little bit this task. So we need a scene function of 5,000 time steps. So just a repeatable, some kind of interval. It even doesn't, it's not that important what is the interval. So I want you to do this code and drop in the snippet of the code in the chat maybe, or like you can share it through the paste bin or something. And the way how we're gonna display this as well, we can display it, let's say, you can add some code here, plot self data, and let's display first 500 steps as it is in our rollout. Maybe you can even write it roll out, and plot show, and then we'll kill the app here, exit. So if I run this function now, it will not produce anything. Maybe I can add some kind of, oh no, it will not work like that. Maybe I can add it like just np arrange. Now it should work if I run it. So, but this is not, so I'm just asking very simple stuff. Please implement these lines to generate the sinusoid function. Now it's not generating sinusoid function, it's just generating the line. So we'll see who managed to do that first. This is a really simple task. So for sharing the code, I suggest that you use pastebin. If you just use the pastebin, open it here, right? You can just drop in for me this part of the code, right? When you finish it, and what was the next that I need? Seriously, I need to log in to do this. That's a fail. I thought it was possible to do immediately. Funny. If somebody knows some tool that I don't need to log in to share the code, please share it also in the chat. Meanwhile, I will look myself for that kind of tool. And meanwhile, you also please finish the small task. I guess there are a lot of tools like that, but the one is that I quickly found is zero bin, where you just drop in your code, press submit, and then you get your link, right? So if I have the link, what is this? Boy, it is so hard. Maybe I need to make a tool that that you can just share the code. I guess you can use this link, hopefully. So yeah, it works. So just copy the link above and drop in the chat, please, when you finish this. Nobody has yet done it. Very strange. Did I make some major mistake in the task? It's very simple. So okay, let's start writing. So is anyone trying to finish Sinusoid? Plus, minus in the chat, and also if the minus, then please tell why are you not doing the task. Also, if it's hard to follow the video, remember there are tools that you can copy your screen and like picture in picture, add it in on the side of your code. That can be useful. Okay, at least one person is trying to finish it. Let's wait for him, and then we'll move to the next part. So I need just 5,000 samples. So the shape that I want is following. So let me show you the shape. So nice that you already have some questions at least. So the shape will be the 5,000. So let me check if there's, yeah, the unsqueeze is here. So this is going to be very simple shape like that. So I want that kind of shape. Very simple stuff, really simple stuff. If somebody wants to make interesting periodic function, that would also be cool. If you can share some interesting periodic functions, I would like that a lot. I was not expecting that we'll do the sinusoid function so long, but that is really simple stuff. Still waiting. Who's gonna be the first one developing the easiest function today? Meanwhile, maybe I will prepare some other stuff. Yeah, Christopher, if you did it, please share the code maybe in the chat, or did you do the whole thing? I don't know what's happening. Also, I'm again start writing the code. It's like strange that it takes so long, but let's do this then. Okay, so so we can write the just the sinusoid stuff very easily. So let's have the x variable, right? So this we can, let's see if this is a torch. So maybe I forgot to mention this should be torch, but doesn't matter. It can be also numpy, and then you can convert it to torch. It doesn't matter. So but we can write torch linspace, right? So this is just like generating floating point numbers in a range of, let's say, 0 to 500 as a floating, and then let's say 5,000 time steps like that. And then what we want is to have the sinusoid, right? So again, if this is a torch, we can use directly torch. The x, the fun thing is that it will work with matplotlib because the torch and numpy have very similar array syntax. So that is okay, I think, like that. And if I run it, it should produce nice sinusoid. Yep, so that's working. So I will add this part to the Jamboard. If some, like it literally took like 10 seconds, but I guess there was some problems. Not really sure what was the problem. So I will add this one to the third slide. So what we're going to do is we'll take a small input of this sinusoid, and we'll predict the next time steps. So we'll take a few time steps and then predict the next ones. Also, the interesting thing, let's see. So if we have the input of, we have the, what will be the 50 these things. So maybe we can look at it. So no, not like that, but let's say what will be the input if this is a, or we can just use the sequence length like this. If I run it, so the input for the model will be actually following like this. So then it will try to predict the following stuff. Maybe we can even make it the task a little bit harder for the model. Let's feed only, let's say, 30 time steps. Something like this, and then it will try to predict the next 500 time steps. So that is the plan. So I just played around a little bit here. If next thing is that we need to comment out these lines, of course, because they are just for debugging, right? This is not for the actual stuff. Okay, the link didn't show up. Interesting. Maybe maybe the YouTube is somehow blocking some links. Not sure. Anyway, if you post the link, then please write that you did it, or maybe, I don't know, like if you find out that some domains are blocked, or maybe just copy the code directly in the chat. Sorry for that. So anyway, the next thing, there is also that here at these lines I added specific code that you can add noise to the output. That is also interesting experiment that will mess a little bit the model and also maybe improve it a little bit, because if it learns very precise values, it will fail when it starts to predict something that is not precise, right? So then we go to the RNN cell, and there starts the interesting stuff. So the interesting stuff about the RNN cell, so we need some of the parameters in the first slide. So let me go to the first slide, and then you will write the forward pass. Actually, I will just give you the parameters. So you have U, V, and B. So the other part about this projection for the output, please don't make that right now. So that is for actually included in the next layer. So if you look at here, that in the model we have already a linear layer here, right? So this is going to do the job of that projection. But the first projection, this RNN cell goes here. So, and to do that, I'm not sure, did we ever try to, I think we tried to make some of the model, the parameters as well ourselves. Not sure exactly when. So here there will be the what was the names of that, U and V. Okay, so U matrix, and actually I will have questions right now. So the U matrix. So the U matrix will be for the inputs, right? And this will be torch and then parameter. And we'll have this one as torch float tensor in the size of. So my question will be, what will be the size here? And it will be uniform, initialized as uniform. But my question is here, what shape should I add it here? What shape U matrix must be? So this is first question. You type in chat, please, what shape should U be? And for V as well. And let's make also for the B as well. So B will be zeros, right? So we need to know what shapes are these three parameters. And you can see up here we have some hints, but please let me know. So I will ask in the chat. So what shape is V, U, V, and B? Yeah, so you can write it, let's say, in U shape is something, and then so on. So please do that in the chat. I will wait for some answers. I definitely know that some of you should be able to understand this. So if I just copy the equation in LaTeX as well, here, right, so you should, looking at that equation, you should immediately be able to write these answers. So please do that. Remember, the previous question took us 10 seconds to solve. Christopher is typing something that, okay. So think about it, what kind of sizes are there? Like the X is the input size, right? The H is a vector of the hidden size. So what these matrices should look like? Should I give you more time? At least Christopher's tried to answer something, and then maybe you can answer at least one of them. So those of you who are like looking at the equation, if you feel confident about some answer, maybe you can type in some answer at least, because otherwise I kind of feel that I need to explain again everything from beginning if you look at this equation and don't see the shapes. Or maybe you have questions. Maybe you can ask some question in regards to those shapes. So the Lee is giving one answer regards to B. That is correct. First puzzle piece is finished. So the first puzzle piece is hidden size here. Hidden size, right. So let me also double check that the syntax is okay. I think it is. But so first answer we have it already. That's good. So then I see another answer. At least thanks for trying. I rather see some wrong answers than no answers at all. But also I like that at least Lee tried the one that he was confident about. So the one thing, so this is helping me actually a lot. This is helping me a lot because when somebody of you answered this, because now I see that the Christophers is telling me that the weight and U and V matrices basically are separate for every sample in the batch, basically, and even maybe into the sequence for every sample that is separate. That is really surprising, but let's look at it. So then we're looking at U, for example, here. So we know the size of the X. So that is first thing that we know, right? We know the size of the H here because that we know also the size of the B now. And in order to this to be executable as the addition, these products of this and this must be the same, and also this, of course, right? The other thing that from the answer in the chat of the Christophers, it seems like that he's telling that the U here, this one, this one, this one, this is duplicated many times, but this is not true. This is just one same U. There are not many U's, there is just one. Just one U that is repeated all the time, the same one. It's not repeated over the batches, it's not repeated over the sequences, it's just staying all the same U for every sample in the sequence and in the batch. Is it clearer now or not? Can you try to guess again the shapes? So let me check. So the Ali is saying that the shape would be so I'm not understanding the idea about the U shape on the Lee answer, because it should, so think about it. So if we didn't have this item here, if we cross out the middle item, this we know is the shape of hidden size, right? So let's add some information here. So hidden size shape. So we know that this is in that shape, right? Or maybe we can even, I could do something cool. I can do like that, right? So this is a hidden size. We know that this is also hidden size, right? We know that this is an input size. Input size. We need to understand what are these two shapes here. So what is this shape and what is this shape? So I don't see here any number of 1. So of course let's say the input size can be 1-dimensional, but I don't see here like the number 1 anywhere. So we should operate only with what we have here. So we also, of course, as Christopher's pointed out, we also have sequence length, right? And we have the batch size, but as we discussed just yet, most likely these two should not be used, right? Because we don't repeat the weights over the sequences and to the I mean, like, we're not having the new weight for every sequence element or for every batch element. We're having the same weight for all of them. If this so how can I try to explain it even more? So if for all of these guys we have only one U, there are not many U's, there are just one U, just one W, just one V, right? So for all of them, just one. For they all share one single U, V, and W. So we still not answered the question. I think you're close to answer. Please try. So maybe we need to think about the linear layer. See here the linear layer, right? Remember in the very beginning we wrote a lot of numpy stuff with the shapes. So that was for the reason, because you need to understand how the shapes work, you know? Like what kind of vector you can do the dot product, like with what kind of shape of matrix you can do the dot product with what kind of vector, you know? Any ideas? Any more ideas? Okay, yeah, maybe we need to move on. So, I really I hope that I'm trying my best to explain it in some good manner. So, okay, Christopher is giving some answer that is interesting. So let's see. So maybe Christopher's misspelled some letters, because the answer is not bad, but the letter is not good. So if he's saying that V, so the V is here on top of these things. So in one sense, maybe the answer could be correct, but in general, we need to have the shapes for the U and W, not for this guy. For this guy, basically, if the output is the same shape of the X, and if we transpose your answer, then this might be okay answer, but in general this is not okay answer. So what about these two guys? Okay, so we waited for a long time. I'm starting giving you the answer. So that here we can only multiply something, but if we have the columns the same size as the that vector, so that means that we will need to have input size here, input size, and comma hidden size for this guy, right? And then let's have the last question open. So what is the shape for this W? So if I give you the answer for the first one, for the second one, you definitely be able to do that. So V shape. What is the V shape? W shape, I mean. So this was previously not clear for a really long time. I don't like this color, but leave it like it is. Yes, Kirill, thank you. Kirill always, when he follows the things, he can quickly get the answer. Like when it's like everything is already on the table, but it's not bad. Not bad. Like basically, it's better to have answer, not to have at all answer. So this is correct. The only way we can then proceed with this equation is that this is the hidden size by hidden size. So is it clear now? Hopefully it is. If it's not clear why it is like this, then please write in the question and I can try to explain it more. But basically this is the correct answer. So we'll move on here to the code now. We don't have much time left. We need to work faster now. So I was again not expecting that this will take so long, but it was good that we did it because now I understand that you have some problems of understanding this stuff. So hidden size, then this will be the hidden size by hidden size. And now we need to implement the equation here. And in order to do that, let's make it more interesting. So I will add to the Jamboard this part before implementing that equation, because I want you to implement that equation and see immediately the results, so that you like it to be interesting to solve that, because that's really easy stuff again. So what we need to do then is go a little bit down. So maybe I will also share the Jamboard, just a second. So in the Jamboard I added on the slide number 3 this initialization part. Let's leave the forward pass for now, not touching it, but if somebody knows how to implement it, then that's great, let's do that. But meanwhile, let's do the other part. So the other part is that we need to implement the for loop. So for every cell, we will go by every time step like this and call the hidden state and the x to the cell, and then the output will pass to this linear projection that was previously described with the letter V, like that. And this is going to be our model part in this case. So this can be in different parts, but let's say in this case it will be in the model. And I will show that in front of you because you're going really slow, and hopefully the last part then it will be fun for you at least. So if we go to the model RNN here, right, we need to implement that small bit of code. That small piece of code, we can implement it. That is not too difficult. So here, this will be that for loop that we need to do. So we will have the H, we're having it already. So there will be the, let's see, let's see. So the predictions will be that one. So let's write here will be the H sequence. So there is all of the H vectors. That would be very useful if we have multiple layers. And we will actually get it back through the this last part. Okay, so for loop for time in range of x size of the dimension of 1, because we have now here dimension very typical for RNN's batch, sequence, features. So there is again a little problem maybe. Let me check, because we need to go over the sequence dimension. Let me check if it is the truth. So there's batches. Yeah, there could be multiple ways to do that, but let's flip it a little bit. Sorry. So I don't like having this shape in the wrong order, because it might make it a little bit confusing. Much better I like when you permute this to have the sequence as a front in the first part of that. So what we can do is X sequence. This is again very common thing in the RNNs. So you can use the permute and change the order of the dimensions, like transpose it. So we want sequence first, batch features. If you use default implemented like these versions of RNNs inside the Torch, you must be super careful about this fact, because they have sometimes you can have batch first, sometimes you cannot have. So here we go over then the size of 0 over the sequence, right? Line 88 is so let me check, maybe I did a mistake. Yes, I did a mistake, sorry, and that's why I was telling somebody like Christopher's that he was using the wrong shape. Sorry for that. Kirill corrected me. So this is actually W there, so I was not careful about that symbol. That is great that you follow the code. That is excellent. So I will update this in the Jamboard. You're right about that. And then I guess the Christopher's also might be right. Let me double check. No, but the equation was, the shape was not right anyway. So anyways, so here, if we go back to the forward pass, right? So we have this guy ready. So then we have RNN cell as well ready. That is cool. And we want then to call the RNN cell and predict the next H. So the H for every batch will be the same. Yeah, for every sample will be the same. So forward, and here we'll pass the we'll need to pass the exact X of the time step T. And actually we can maybe do this in some smarter way. Yeah, so the smarter way maybe would be not to use as a range, but anyway, we can do it that way as well. So X sequence of T, maybe it'll be clearer like this. So like that, and H, that's cool. So we pass H in, we get H out. That is what we need. then we actually could call all of the linear stuff at once. We don't need to call it like step by step actually. So what we can do is here append h of our predictions. So that's why it's called recurrent neural networks, because we have recurrence here. So we do that. Then we will do the stacking. So let's see. So this is going to be then the th, well maybe it's not clear, but h sequence stack, and this can torch stack of these guys, and then we need to permute them back. So the h sequence stack, we could, I think we could get it out here. Let me double check a little bit what was the code down the line. The last hidden stuff is here. I guess that is not what we need. The h will be fine here. The h will be fine, and the stack will be needed just for the linear projection. So we can then have the h stack back as a batch first, so we can permute it. X permute as 1, 0, 2, and now we get it back to the batch sequence features. Maybe I can also make it clearer. I can add here input size, right? Here there's an input size, and here there's a hidden size actually. So now we have it like this. And the last thing is we need to do the projection. So the accept, no, it's going to be fine, I think. It should be fine. So forward, it will work by the last dimension basically. The h stack, like that. Oh, sorry. Like that, okay. So, and I will also make some dummy function up here just to make sure that everything works. So let's have it as torch ones of the size of hidden size. So that is what we wanted to output. Maybe you can even store it hidden. I will just in a second I will show the code that I made with the for loop, but I just want to make it sure that my for loop is correct, so there is no bugs, you know. So if I add a breakpoint and try to run it, so if it will be okay, then you need to implement only the last forward pass, and it should be ready to test it out. So let's see. So if I go here, it works so far. So let's see if it works so far. Yes, it works. So what is this size here? So the 30, interesting. 30 time steps, right? Something is not, I think, as I wanted. H size, 8. Okay, yeah, my bug. So, but there is no bug in that part, but I forgot that we need to have batch dimension here as well. So we need the batch dimension as well. So x size 0. And then let's test it again. Meanwhile, I'll check the chat. Nobody is screaming yet. So, okay, let's see the shape. So now the H sequence shape is like that. That's cool. Then the next shape is so the 30 time steps, 32 batches, 8 those guys. That's great. Then the predictions afterwards are a size, or so 32 batch size, 30 sequences, and 1 prediction for each sequence step. So this is correct. This is correct. So the for loop is ready. These 2 lines of permuting, very important for the RNNs. Keep reminding, keep like focusing on them. Don't forget about them when you try to make the RNN models, because of course you need to like change the so you need to go by every batch, every time step, like because the next time step is depending on the previous time step. If you don't go step by step, you cannot have this memory inside there, right? So this is what we have there. So I will add this as well in the 3rd slide. And now, so let me show you in the 3rd slide. So now we'll came to the last part of actually implementing the last equation, very simple equation. So see, I added this forward pass here. The forward pass is here. And now let's see who will first implement the last equation here. So the last equation that we need is this recurrence equation of the cell that we looked at the very beginning of this session. So this y prime, of course, is not correct. So it must be something else. It must be, basically, we can write it here as y prime, right? So please implement this equation as with Pytorch, and let me know when it's ready. Also, please then, first of all, what you can do is submit your code in the classroom, or also maybe you can just copy this 1 line in the chat. That would be really good. So, and if this part will be ready, then you will see nice pictures starting to appear of the rollouts and all sorts of cool stuff. So, is anyone trying to complete this equation? Plus, minus? Great, I like that Kirill is trying to do that. This is not hard. I really say that this is not hard. Just look at some of the examples that we did before. So you need to do dot products, right? You need to use this arithmetical addition, not hard as well, right? I think like if you just know the syntax, it should be like also 10-second job. But of course, maybe I have some bug or something. So what I do, I'll copy this part out and put on the Jamboard. Meanwhile, quickly in 10 seconds implement that line and check if I don't have some other bug, because last time I think I had a bug and then I was waiting for people to complete. Oh, nice. Lee is using the new cool syntax of the dot products. Yeah, there is one cool syntax that you can try to use. So he's asking about h t minus. So this is, if you look at the equation down below, so let me check if what I'm showing. Yeah, so here this is the previous time step in very beginning, because it's initialized the zeros here in some other part of this code, and the ht here is time step plus 1. So here the h is here is h, so this is actually ht minus 1, and the output of here is actually the ht. So also in this equation, this h is t minus 1. So yeah, maybe I can just delete this part. So I think your equation should be fine. So Lee is the first one who dropped it in. So I assume that others are also trying. So we can try out with his cool syntax. So I copied his version. Let's see if it works. But there are other ways how to write this thing. With matmult, of course. So if I run it. Okay, it cannot be multiplied like that. It must be in different order. So you can do different ways. Either you can transpose things, you can say t as that, and then you need to transpose a lot of things. Basically, other way, I think you can just flip it around, hopefully. I'm not sure if it'll work with this syntax, but you can try out. So if I run it, okay, now it works. So it trained so far, but then there is a small bug again. Okay, so that was what I was talking about. I was thinking that maybe something is messed up. So let's see. So the training part worked, the rollout part failed. That was not expected. So in the rollout part, I think there is something that I forgot. The H hidden is coming out here. I think I don't need actually something of this. Hidden time step. Why do I accumulate the hidden time steps? That is a good question. Why do I do it here? The hiddens. I don't need those hidden time steps like that. I think I can just delete it here, use it without that part and this part, and also if it will not work, I will make a breakpoint and fix it. So let's see. Okay, now it starts working. Cool, nice. So anyway, I will drop in this 0 bin this part of the code, because this part was a little bit different kind of implementation. I did not check it before, sorry for that. So let me create a new 0 bin stuff. So copy. Okay, I'm pasting the code. I will also paste the same code inside the Google the Jamboard. So basically the change was that I removed the selection from the hidden state like the previous code that I based this one on was using that the hidden states were returned for the whole sequence. So you can do, for example, the next layer. So if you have the next layer, then you would like to return the whole hidden state sequence. But if you don't have only one layer, you don't care about all that stuff, because the next layer actually will feed from the previous layer's hidden state. So if that makes sense. So I shared these lines in the Jamboard, and if I go back to the Lee's answer, it was almost okay, only the the order was not okay. The other thing you can also do is to, instead of that interesting @ symbol, you can use that matmul. So that's basically the same thing. You can write it with matmul. And if you would like to have the same order as in this equation, then you need to either transpose them before or transpose them after. So that's it. Let's see about others. So let's write in. So is it working for you? Working for you. So if it's not working for you, then please let me know what exactly is not working, and I can help you out. So if I run it again, so now it starts learning the sequences. First, epoch cannot learn anything, then it starts to learn some shape, right? It starts to become something a little bit like that, and stuff like that, right? We can also make the code harder for the stuff, so it starts to become better and better. So of course it's not perfect, but it seems to become better. So I see some of you are getting this work, so that is cool. One thing that we can do is add the noise. So let's add the noise. So uncomment these lines. Maybe they will become more robust. So great that I see that Christopher's. So yeah, the shapes are actually not off, Christopher. Just change the orders, it will be fine. You can also so depending on the initialization, it can be different way. Okay, the noise, I guess, is too aggressive because now it cannot learn anything. Okay, noise, let's remove noise. but if I remove noise, then it's okay. Maybe another cool stuff we can do is make it a little bit interesting, a periodic function. So now I have x, maybe I can add x1, x2. You can create your own periodic functions, like even more interesting maybe. So if this is going from -1 to 1, we can drop in maybe in 1,5, let's say. Then we can what we could do, we could create something crazy. So torch abs torch cosine of x2, and then let's scale it a little bit to 0.5, for example. I'm not sure, no idea what will happen. Let's see. Oh no, I have mistake, x1 here. So let's see what kind of periodic function I just invented. Okay, no, that was not what I wanted to see, because I need to extend this a little bit. So let's say rollout. See a little bit longer sequence. Okay, now this looks interesting. What else we could do? Maybe we can flip it to the same, because maybe I just added at the. Oh, okay, that looks interesting. Yeah, I like this. So we have really crazy periodic function now, and we can throw this at this model. Also, we can increase the hidden size. So let's say 32. Maybe I will also add this one to the Jamboard, so you can try out. For the homework, I will give you to implement another type of RNN architecture. So you will need to change only a few lines, but you will need to understand what you're doing, basically, otherwise you will not be able to do that. So if I'm trying now to run this stuff, so we'll see what happens. Okay, it's very hard for the model to learn, I guess. At least it learned the first part of the function. Maybe it's too hard. Oh no, it started to learn something. No. Okay, it might be too hard. Oh no, it's good. Okay, we can maybe make it a little bit easier by adding it a little bit longer sequence. So maybe add 50 steps. Let's see what happens now. Okay, it tries to learn. So this is not the state-of-the-art model. Definitely not the state-of-the-art. But hopefully it could learn something. Okay, epoch 12 still not able to do this. And just the experiment, what happens if we drop this complex part and just leave the very simple sinusoid, run it again. Okay, first epoch not working, second not working. Then trying to get something. Trying. Okay, now it looks a little better. Okay, now it looks interesting. Okay, it's still, the model is quite weak stuff, but at least it's trying. So even the basic sinusoid, it is not easy for the model to learn. I'm not sure exactly. So after about 20 epochs, something looked normal. So the one thing is that you must keep in mind that, oh, now it looks good. So about 20 epochs, it works good. So about, let's say, about 20 epochs, then it converges to the function. So if you add some interesting functions, you can try to learn those functions with another function. That's a cool idea, right? If you know that the output will always be from -1 to 1, you already know there you can use some small hacks by adding something after the linear layer to improve the output. Of course, you already know how to do that. So yeah, so that's about it for today. It was more challenging than I was expecting. I guess not so easy stuff for if you see it the first time. The next time, so for the homework, I will give another architecture of RNNs for you to implement. And for next time, I think we will do one of the things, so either instance segmentation, either the GANs maybe, or maybe reinforcement learning. So I don't have many workshops left before I will start doing some stuff with the university again. So, but if there's some part missing that is needed for your research, I will provide it to you. So hope this was fun. At least we managed to learn the sinusoid function and managed to create interesting other functions. Yeah, so meet next week, okay?